Okay, it's a Sunday, so that means it's time to record a video of whatever this is. What this is the magnetic AB, that's in screen, that's in focus roughly. Magnetic AB receiver 8801A. This is a NMT 450 analog mobile telephone receiver. NMT system was used in Norway, Scandinavia in general, and also the Netherlands. I'm not sure where else it was used. It was in use from the 80s until actually the middle of the 2000s in some sections. I think it was actually turned off for the last time in 2007. So this is part of the base station receiver for the NMT network. Now the NMT network was a full duplex radio telephone system with in-band signaling and automatic roaming. So for its time it was quite sophisticated. It used straight analog FM in order to transfer the audio with an 8 MHz split. And as the name implies, it's operated in the UHF area around 450 MHz. The split was 8 MHz, and if you look in mobile telephones that were used with it, they were quite large. Obviously, they were more like luggable than portable. They had duplex filters that were actually quite large compared to the overall volume of the device, although with 8 MHz it's not as ridiculous as you get with an amateur radio split of, say, 2 MHz at the same frequency band. So I'll just open the cover here. Normally this slides out, of course, but I've already loosened it. Just put that away. So this is one I've been modifying in order to operate in the 70 centimeter amateur radio band of 430 MHz. And I was given this receiver just to see what I could do with it by another amateur radio operator. So this is actually a pretty neat layout. If you're not familiar with radios, it might look a bit strange, but the layout's actually quite nice. It supports a remote control interface because this is a channelized system. It doesn't have direct frequency input. So I'll just let you see the front panel first. There's a channel selector here, which is a thumb wheel, and it goes all the way up to 199. You can get a 9 there, but that doesn't actually change anything internally. It's just one wire connected to it. There's there's a remote control interface selector. There's an analog squelch control. Because this was analog FM, you needed a squelch. Got an AF output, local oscillator indicator, a button which doesn't seem to do anything. You can't really see it. There it is. I have no idea what that does. And an antenna input. This would come from the duplex filter. Now I've added this SMA connector on the side because I'm planning on building this with the associated transmitter into a duplex repeater for amateur radio use, probably D-Star, digital voice. So I'm planning on putting a TR relay for now in here somewhere in order to run it in half duplex. But that's a whole nother video, you know. So basically it's a double super heterodyne receiver. And I'm not going to go through all the basics of how a receiver works, but basically the antenna port comes in here on this BNC, which I can connect up like that. It goes through a couple of filters, which tuning these for 430 MHz is also a whole other video. But looks like I've got some screws loose on this one, so I can actually take that off later and show you what it looks like inside. These are helical bandpass filters, and the purpose is to ensure that the signal path, which is through here, through this little can here, which has some passive components in it, then through another set of filters, producing 6 helical coils that resonate. They let through the audio in the formerly 455 MHz range and prevents the transmitter frequency, which is 8 megahertz down, I think. Doesn't really matter. It prevents the transmitter frequency, which is very near, it's connected to the same antenna through a duplexer, from leaking into the receiver. So these are very important for sensitivity, and if they're not tuned right, you have no sensitivity at all. There's a mixer, that's that thing, it's an MCL Ray 1, and this appears to be some sort of quarter wave stub. I have not really worked out what that's good for, but I suspect I may need to retune that by just replacing it with a longer piece, since I'm going down in frequency. And the local oscillator is generated on this board, and it's then generated in this VCO here, which you can see. And then it's doubled in frequency, transferred over this coax into an SMB connector, then doubled again in here. This bottom can here has a transistor in it, and that's a doubler. And then 2 filters to prevent the lower subharmonics of it. Normally this would run at 430 megahertz. You'd then have 215 megahertz, which is half, because that's what comes in here. And then you'd have half of that again being generated here. And that would all leak through and would make it sensitive at 2 additional frequencies. So this filter just gets rid of that. The output is a 21.4 megahertz signal, and that goes over this coax into this quite large and very complicated board with some sort of very complicated squelch circuit that I haven't quite worked out, as well as these cans, which I also have no idea what they are doing. If anyone knows what those things are, please tell me. There's about 6 or 8 pins on the bottom, and I can't open those. I've tried. Regardless, I don't think I'll have to do much to this board, except maybe replace this filter here with a narrower one. I've been thinking of getting an 8 kilohertz wide filter, because I can get those quite cheaply instead of this one, which is a 25 kilohertz filter. That's just to improve adjacent channel rejection when used in very narrow band communication. But the main topic today will be this local oscillator board, which is currently not really working all that well, because I broke it. But it wasn't working all that well before I broke it either, and I was in fact able to modify it. Although I'm not going to tell you detailed instructions of how to modify it, because I have a different method I want to use, which involves replacing a lot of this circuitry here for some more modern microprocessor controlled circuitry. And I'm also going to replace this 4 megahertz oscillator with a 10 megahertz one, so that I can run an external reference if I want to. Additionally, I'll give better frequency stability. So what I'll do is I'll pop out this board and show you what it looks like. Okay, this is the local oscillator generator board, and the way this works is a standard PLL synthesizer. It accepts a BCD input here, and this special chip here has a set of inputs that let you decide that, a 0 in here will give a certain division ratio here, and then if you put a 1, that'll give this division ratio plus 1. So you can have 2 sets of input, a binary preset input and a BCD input that's then added together to give the final division ratio. Now, if you're not familiar with a PLL or haven't worked on them in a while, that's probably a bit vague. So you need a block diagram, such as this one, which I prepared earlier on an envelope from my bank. But I don't need the envelope, so don't worry. Basically, I'm going to try to go through this. You need the output here. That's 215 megahertz or thereabouts normally. It's a bit lower in my design when I've retuned it. That's doubled bandpass filter sent into the mixer and combined with the antenna signal. And this is all on the other board with the filters. So the topic of this board really is the VCO. That's a voltage controlled oscillator, and that's controlled by a PLL circuit. The two things that need to be changed are the frequencies that this thing operates on. You can change that by adding some capacitors in the right place if you want to lower it, which is what I want to do. Additionally, you need to change the division ratio n in order to lock at the correct frequency, which is now going to be lower than it was before. Now this circuit is slightly different from many other circuits in that it uses a 4 MHz time base, and that's not really all that strange. But it's then multiplied by 26 in a transistor circuit that's inside this can here. And then you get a 104 MHz signal that's mixed with the VCO output here. There's also a little SIP gain block. That's what this orange thing is, according to the schematics at least. So the output here is about 104 megahertz, or 110, or thereabouts. That's then subtracted. You subtract 104 megahertz in the mixer, which gives a signal of typically from 0 to 4 megahertz here, and that's fed into the divisor, or the divider circuit, which is inside this IC. Which is impossible to replace, by the way. And then the division ratio here needs to be such that this frequency here, which is a direct consequence of this frequency, divided by n gives you the correct frequency here, in this design 6.25 kilohertz. And that frequency is then compared by a reference frequency generated from the same time base, and the time base here of course specifies how accurate the whole system is. So the divider ratio here, I think it was 625 in the original, although I may be mistaken there. It's something around that. That gets you a 6.25 kilohertz signal here. It goes into a phase comparator, which is also a frequency comparator, so it senses if with this frequency fixed, is this frequency above or below this frequency. Then has an output, which is normally a square wave, that's filtered in what's called a loop filter, which is typically an integrator or maybe just a RC filter. Never mind that, that's a radio in the back there. Anyway, that's then turned into a DC control voltage, which is fed into the VCO in order to change the frequency. So if this frequency here were to drop, this frequency would drop, and you'd get a positive output here, which would increase the frequency until the whole thing stabilizes. The loop filter then becomes quite important to make sure that this circuit actually becomes stable and doesn't oscillate back and forth or have other issues. And this N, of course, is selectable through the thumb wheel. That's what you actually set with it. Now the problem with modifying this thing for ham radio is primarily that this mixer here causes a problem because the frequencies we want to target here are now below this frequency instead of above it. So we want to actually have a frequency here which is about 102 up to 104 ideally, although I've been satisfied with 102.7 to 103.7 to cover the range needed for a duplex repeater. Norwegian allocations are 430 for inputs and 434 for output frequencies in the 70 centimeter band. We can cover that quite nicely. But anyway, it causes a problem because when you go below this, the frequency here, the filters in the mixer don't really work all that well. And it's just not a great solution. You have to trim this quite far down in order to make sure that you can't end up above this frequency. What would happen is if you can change the polarity here and make sure that the direction will be reversed when you change this frequency to work below instead of above the frequency. In that case, if the frequency here decreases, it'll move farther away from this, which will actually cause this frequency to increase when you're below, and normally it would would decrease as you lowered, because it would get closer to this. What would happen if this thing were able to cross 104 in normal operation is that you'd have a phase reversal and the whole circuit would probably just lock up. And that's just no fun. That'll ruin your day. So I had some problems. I was able to modify this circuit, this N here, and the VCO in order to lock at the correct frequency. But I had a lot of noise on the local oscillator wave, so it just made the receiver perform like garbage. It's just not a nice signal on the output. So my plan is to just ditch, actually I'm just going to ditch everything but the VCO and take all this stuff and just remove it. And then I'm going to use an IC made by Freescale, which is serial programmable, so I don't need all those BCD lines, and a microcontroller in order to just set this frequency, and then it has all this other stuff internally, except the 10 megahertz input. I don't need, or I'm going to use a 10 megahertz input instead of 4 megahertz, because that's a nicer frequency to work with. And the loop filter I'll have to recalculate based on the performance of the rest of the circuit, but that's a whole other video. VCO I'm going to keep just because it works. I already retuned it. And the rest of this stuff as well I'll probably just keep. Okay, well that was really interesting. Now let's take a look at this. I'll just have to go and get a screwdriver because I forgot mine. Oh, there it is. How could I have missed that? Well, anyway, I had this thing at work in order to tune the filter, so I forgot all the screws to this one at my desk. And I've been forgetting to bring them home for about a week. So we can take a look inside this filter here and get a good look at my hand too. So this is the filter for the local oscillator frequency, which had to be brought down in frequency by quite a bit, about 21 megahertz in fact. And that's way outside the tuning range of these things while they're unmodified. And the helical bandpass filter basically works by having this helix thing, which is resonant somehow. I'm not that well versed in the physics of this device to really tell you how they work, but what I do know is that the amount of metal you put inside here with these set screws, which are very carefully tuned and usually with lots of Loctite on, determine the resonant frequency, but also the number of turns determines the resonant frequency. So you can offset it by adding a capacitance to ground, or just some mass, depending on how you want to define it. Now I spent a lot of time, like 4 hours, trying to tune these things using longer screws and bigger screws and adding nuts and bolts to them, and just wasn't getting anywhere. So what I did was I ended up just scraping off a bit of the enamel here and soldering on a half turn of extra wire. Not even that, just less than half a turn. And that was enough to bring them down to about 20 megahertz, from 450 to about, an open case frequency with no metal in them. They were resonant at about 500 megahertz originally, and I brought them down to about 450. So I was able to tune them for 430, and this one is resonant at about 430 originally. So I brought that down by about as much, and I was able to tune them with actually almost all of the original set screws. I did put a longer one in here just to get it tuned properly. The actual mechanism for tuning these is extremely difficult unless you happen to have a just thinking about it, I really shouldn't have opened this because now it's probably going to be slightly detuned based on how I position this cap back on. But yeah, I'm sure it'll be fine. So the method for tuning these involves using either a network analyzer, ideally, or if you don't have that, really the only way of doing it is to use a spectrum analyzer. You could, in theory, do it with like a RF voltmeter, but it's not a good idea, honestly. It's quite painful to do by hand. what I used at work was a spectrum analyzer with a tracking generator, so I just connected the tracking generator on the inputs and then connected the output to the output, and it was tuned for maximum response, because what you see then is where each of these are. They've changed slightly based on how the other one's tuned, but not a whole lot. But you can actually see each peak lying around. You see a peak and a big peak and then a bunch of small peaks, and you just have to sort of turn these in order to bring them all into the same frequency. Once you have them at the same frequency, then you'll see that they peak and you get a tremendous boost in coupling at that frequency, and hopefully it's the correct frequency. So these filters ended up being very flat over about 4 megahertz, which is excellent, because that's the range I'm targeting. So one last thing I'm going to show you before finishing this up is just how you can use some very commonly and available and very cheap devices in order to just check what frequency this setup down here, the local oscillator, is running at, and confirm that it's running and check if it's noisy or not. And I'll have to reset slightly in order to show you that. Okay, it's probably going to be slightly hard to see the screen, but I don't feel like installing screen capture software just for this tiny segment. So, and yes, that is literally a Surface Pro. If you're wondering, I am stupid enough to have bought one. It's quite a nice piece of hardware though. But the buttons are quite easy to break, unfortunately. What's connected to it is far more interesting though. Let me just move that slightly. You can see a nice reflection of my kitchen. That on the end there is a SDR dongle. And I've modified mine slightly to put a BNC connector on it with lots of hot glue and some self-vulcanizing tape. It's running SDR Sharp right now, which is a software-defined radio decoder, and this dongle can receive anything from about 25 megahertz all the way up to 1.3 gigahertz, I think. Some models go higher, some go lower. The local oscillator in this device runs at 102 in the case of my retuned edition. It's also being doubled, so it'll run at about 204 up to 208. And you'll see twice that again up at around 410 megahertz. So one way to do the receiving is actually quite simple. You can just use a device like this, an ICOM transceiver, although it doesn't have to be an ICOM, and just go in there and tune it and just sort of look around. We know it's going to be at around 410. So this one has general receive, and you can just sort of look around. I think it's going to be somewhere around here. Apologies for how boring it is to look at me fiddling with some knobs. And surprisingly, I wasn't able to find it as easily as I thought. Usually it's not that difficult. Let me just check here. 408.8 something. Ah, there it is. That is the local oscillator, which is the receive frequency minus the first IF frequency, which is 21.4. And as you can hear, it's quite noisy, and that's part of the reason I wanted to fix this circuit. But this doesn't work when the local oscillator's outside of the tuning range of a commercial receiver, and it can also be quite a pain to find this frequency if you don't know what it is, which is often the case if you're working on some unknown piece of equipment. What we're going to do now is we're going to take a look at the SDR receiver, which you actually just saw me cheat. You saw me using it to cheat in this test. We're going to start by looking at, let's look directly at the local oscillator. You can actually see that peak there. And You can actually go ahead and decode it. You can zoom in here, and what you can see in the waterfall there is how noisy it actually is. And that's a problem with both the power supply and some other issues. Ideally, this should just be a straight line. Don't trust the frequency on this SDR dongle though, because it is awful. You will have to trim the frequency after it's warmed up by generating your own carrier or tuning to a known frequency, and then going into the configure menu, which is there, and then just selecting how many ppms you want to correct for. You can select the frequency up at the top, right around here, and just change it until this peak lines up with the correct frequency. My local oscillator is actually running open loop right now, so it's not surprising that it's drifting quite a bit. And when you have this SMA connector, you can easily connect a small antenna and just put that right around where you expect to find it. And as you can see, I'm severely overloading my dongle right now, so we can go in and just turn down the gain a little. And that's a pretty nice way, because now I know that if I just tune around like this, I better zoom out though, you get about 2 megahertz at a time. And if I just browse around there you go. That's my local oscillator. Let's just put that right around the middle of the display. And if I move my antenna to right above it, I can actually get a very strong signal. And this is with 0 decibels gain internally. You can go up quite a bit. It's also possible to actually get some oscilloscope probes and just probe around in there, because the sensitivity is very high on this device. If I just touch some pins in there, I just touched the control pin of the VCO and I changed the frequency by quite a bit. And as you could see, it's now actually oscillating up and down, and that depends on what frequency that will happen. That depends on quite a lot of factors. But touching that pin will usually affect the frequency if it's not locked. And even then, it may still affect the frequency. So let's just change my frequency there. What you may also observe in this case is that if the PLL loop is oscillating, you'll actually just see a broadband hash across the display. Just be aware of that if you're going to start using this to modify stuff. And this is a very good way of checking just how much noise you have. There's a phase noise, because the narrower this is, the better your phase noise is, because this noise here, if you decoded it as FM, you can hear it, and that'll directly couple into your receiver in FM. So it's not really something to take lightly. You need a good PLL, and preferably one that doesn't drift around like this. But I will be fixing that shortly. Anyway, there's lots of fun things you can do with this. I mean, you can check exactly where frequencies are. Actually, it looks like just me bringing this antenna near the PLL. That's what I'm doing right now. It's actually changing the frequency. And we can't look at the 21.4 megahertz output because that's too low for this device to tune directly. But yeah, I hope to get back to fixing the local oscillator of this radio within the next few months. I may even have the transmitter as well. I've been promised that I can get that whenever I want. And I'll be building at first a simplex D-Star hotspot for 70 centimeters to replace my old VHF system, which I'm currently running. That's all for now. So, bye.